Welcome to note set number 29, where we will cover our first way of designing linear phase FIR filters. And I'll say right up front that this is not the best way to design them, but we're going to introduce it primarily just because it's a good view into what drives the design. And sometimes you just need a simple, cheap and dirty filter design for doing something. And this is an easy one to do. Yeah, everyone should just know about this because it pops up every once in a while. But we're going to look at three different ways to design linear phase FIR filters. And really it's the third one that is the workhorse that virtually everybody uses. But you should be familiar with all the methods. So this is called windowing method. So let's take a look at it. It's covered in section 10.2.2 of Proacus and Monolacus. So once again, we've seen this little diagram before, but it's going to lead us into the ideas behind this particular method. So suppose we want to design a low-pass filter, and we would like it to have a cutoff frequency of B radians per sample. We want it to have linear phase, but we're not necessarily speccing what the exact slope of that is. We'll see what we need to do to get that. So usually when you're speccing filters, you want a linear phase, but you don't care what the slope is. You just want it to be linear. So as we've seen before, we can find the impulse response of this ideal low-pass filter, and it turns out to be, if we put a delta function in, we get a sinc function that looks like this out, and we can select an n sub d so that the center of this impulse response is shifted out some degree, some amount, and we also note that this n sub d is the center of symmetry, and we have the positive type symmetry. So we have that those two are equal to each other, those two are equal, those two are equal, those two are equal, those two are equal, and so on. Notice also that the further out we shift with a larger and larger n sub d, the more and more of this actually shows up to the right of n equal to 0, which becomes available to us, as we'll see, for making this into part of a causal version of this. So that's the idea. We see that this thing is not causal, and we go, uh-oh, we've got a non-causal impulse response. But basically what we're going to do is we're going to turn this into a causal filter by just truncating. First we'll throw those away, and then we'll say, okay, we need to make this symmetric to have the linear phase. So if we're keeping only these things to the left of that center point, then we should keep the same kind of structure to the right. And this has nothing to do with the fact that I'm showing two that go through 0. That's just a weird occurrence that I'm kind of regretting at this moment for having shifted this so that it goes through 0 value at n equal to 0. But so totally irrelevant. So the basic idea, we're going to truncate it, and this will start off with a even more simplified version of this. We're going to do a truncated sinc method. So we compute the sinc function that would correspond to the ideal low-pass filter, and then we're just going to shift it out some amount and then truncate it. And so this last value here, n, will tie into how far out we have to shift it. So if we want the length n, we'll shift it by n over 2. And then we just truncate down here, and we truncate up here. And the filter order is going to be n, because our last non-zero value is at index of n. Therefore, we have 0 out to n. So the filter length is n plus 1. And that connection between order and length is always true for FIR filters. The order is 1 less than the length, or vice versa. The length is 1 more than the order. So B is our cutoff frequency, so we can compute for n equal to 0 out to n. We don't really have to compute all the values and then truncate them. We can decide on an n value, compute these numbers with the appropriate n over 2 in there, and shift away and calculate away. The thing that you should recognize here is that we are choosing n. We have to choose n to be an even number with this the way we formulated this here, but it is possible to apply this for other values as well. So I'm just showing it here with n equal to an even number so that we get an integer shift here, but you can actually do it with an odd, even though you end up with a non-integer shift there. And so these are the values that are going to go in here, the B0 out to the B sub n, and this will be our general form for our transfer function and our general form for our frequency response. And we see that this is an FIR filter, and we've made it causal, and we're expressing it here in a non-recursive form. So all FIR filters can be written as non-recursive filters. Great. So how well can we get? How well will this work? So here's some results for designing for a case of B is equal to 0.6 pi. So that's our cutoff frequency, and I'm normalizing by pi, so there's our desired cutoff frequency. And you can see that all of the designs end up hitting 0.5 at the cutoff frequency. And so that really isn't the definition of where the cutoff frequency is by the real strict definition. So you can see that already we're kind of getting something not quite right on our filter design. So remember our usual definition is 0.707. So that B comes from the definition of the edge of the ideal passband, but in reality we'll be getting a true 3 dB cutoff point, or 0.707 cutoff point, that is going to be slightly less than what our design is showing here. So you might have to go through a little bit of iterative design here. So anyway, we're looking at 3 different cases here. A blue curve, a red curve, and a green curve. So the blue curve is for an order 20, length 21. Red curve is for a length 61, and the green curve is for a length 121. And we can see a couple things here. If we zoom in on this, now I'm going to try something really fancy here. In the past, I've inadvertently done this, moved this thing around, but now I'm going to purposely move this around. So if we zoom in on this, I like this. So if we zoom in on these curves, we can see that as we go to higher and higher order, we get a sharper and sharper transition between passband and stopband. And so that's actually a nice characteristic. And basically we're essentially saying that as we go to larger order, we can achieve better characteristics of our filter, and that is true in general. We'll see that with all of our design approaches. And it just comes from the basic theory that the longer we make our FIR filter, the better we can try to achieve the ideal type shape. Because remember, the ideal filter actually has infinitely long impulse response, in fact, infinitely long in both directions. So clearly making our truncated filter design impulse response longer and longer will allow us to get a better and better response. Now, I shouldn't have been so hasty here. The last thing I want to show you, though, is, let me see if I can get rid of some of this stuff here. No, not that way. Let's try it this way. If we look at the height or the amount of ripple, we see that the amount of ripple actually doesn't get better as we go to longer filter length. And that's a characteristic of this design approach, not every design approach. So, in fact, that's one of the downsides of this kind of truncated approach, is that we're kind of stuck with whatever that level is, and we'll need to go to more clever versions of the design to try to get that to be improved. So here's some general insights. Longer lengths gives a better approximation in some respects. Better approximation to the ideal filter response. So we get a sharper transition, but we certainly don't reduce the ripple in the stop band, nor in in the pass band, nor in the stop band. So we don't really improve the ripple, the worst case ripple, in either pass band or stop band. So we get a better transition band, but that's it. We also see one of the prices that we pay is we get a steeper phase slope. So as we go through the orders, the slope gets steeper as we go up to the longer filters. So remember that the amount of delay is the negative of the slope. So we've got a negative slope here. So the more negative that slope is, the longer the delay will be. And in some applications, that may be a constraint, that we can't have too long of a delay in computing the outputs. So nonetheless, this is a cheap and dirty way to do the filter design, but most importantly, from an educational point of view, it shows us kind of where we're going and what kinds of impulse responses we want, and what are some of the challenges, and what are some of the basic trade-offs. All right, next slide, where I've got some MATLAB code that generated the previous plots. So I won't go through all the details on these, but I'll hit some of the highlights here. I play one little trick here that's kind of fun, and I'll talk about that in just a little bit. So you can see up at the top I specify my B value, and that's the only place I specify it. So I like to, instead of putting in explicit values in places, I like to specify as much as I can up at the top. That way, if I ever want to go and just change to a different value of B or to a different value of N, I can reuse code very, very easily because I haven't hard-coded values in. So, and I'll often try to put all the things that I'm speccing in the very first few lines of the code. Okay, so I specify my B, I specify my N, and then I compute an N index, and then I compute my actual impulse response values. So I don't really have to compute a bunch and then explicitly truncate them. I just compute the ones that I want. Now I'm going to go and compute my frequency, which I normally just put in negative pi to pi with lowercase pi here, and use that. But there's a reason that I do this little trick, and we'll get to it in a little bit. What I do is I take pi, the real pi, or at least MATLAB's finite precision version of it, some number of decimal places. I multiply it by 1,000, and then I fix the value. So fix just truncates it, the value to the next integer down. And then I divide by 1,000. So basically, what I've done is I've rounded pi to the nearest 1,000th decimal place. And there's a reason that I do that. Then I jump by a jump of 0.001. And the reason that I do that is that creates a, let me try to get rid of some of this stuff here. What that does is it creates my omega vector so that it literally has one value that is exactly equal to 0. If I put in little pi here, I will be starting at something that is, a real close approximation to the real value of pi, and then I'll be jumping at 0.001, and I won't hit pi 0 exactly. Now there's a reason that I want to hit 0 exactly, and we'll get to that in just a little bit. Okay, so we continue on here, and so the next thing that I do here is I find, this is just for later, I find the value. So there's a nice command called find, and then you put in some condition in there that you're looking for. So I take my omega vector and I say find the values of omega that are exactly equal to 0. So equal assigns something, equal checks. So basically the command inside the parentheses here will be all zeros except for the one location where omega is actually equal to 0. Then it'll set a 1. And then the find command is going to go through and it finds all the places in its arguments where it's 1, a logical 1. And then it fills this I vector with the values, the indice values where that condition occurs. So at this point, I've got the single number in the variable capital I that points to the position. So I've got in my variable I, I've got the exact pointer to where omega is equal to 0. And we'll use that in just a little bit. Okay, so then I just do a FreakZ. So I do my FreakZ. I put in h for the first variable because that's the coefficients of my numerator. For an FIR, I put in a 1 for the denominator, and then I put in my omega. So there are other ways to call FreakZ, but this is the way that I typically call it. I specify my omegas, I put in my A and my B, and I calculate my H. Now I'm going to plot it. So I do a subplot 2, 1, 1. So I'm going to make 2 plots that are arranged one above the other one. And so the first I do a plot. I do my famous normalized by pi, and I plot ABS of H. And I do a little trick here. This is worth knowing. So when I do a plot, I say HH. Doesn't have to be HH. Can be anything. But I just decided to use HH here. I couldn't use regular H because I've already got that for, or single H because I've got that for my impulse response. MATLAB tends to, in their examples, use H because H stands for handle. So I just used HH. And what it allows you to do is, in your code, set various characteristics of the plot. So, so in this case, I did the plot. I set the handle with the HH equals the plot. So some identifying number goes into HH And when you put that number inside a command called set, it allows you to set various characteristics. So in this case, I find that when I make plots, the line width is so narrow that when you import them into PowerPoint or Microsoft Word for publication, that the line widths are so narrow they don't really show up well in the PowerPoint or in the Word document. So I tend to automatically just go right to line width 2. So that sets the line width, so I get a little thicker line on my plot. And then the next thing that I do is I do another thing called GCA, Get Current Axis. So that has to do with the axes around the plot, not the plot itself. And so I set that to HH, and now I do a set command on that, and I change the font size to 14 because I find that the fonts are a little bit too small for making nice PowerPoint. So you can do all this inside your code. Then I do a hold on so that when I do a subsequent plot for my other filter lengths, length 61 and length 121, I'll put this right on top. So I'll have 3 plots, 3 magnitude plots on top of each other, and then 3 phase plots on top of each other on the next one. Okay, now I'm going to go to the unwrap command and angle. So I compute the angle of H. I do the unwrap to get rid of any of those 2 pi jumps due to the wrapping of the phase that angle just automatically does. I set that equal to phi. And now, remember I mentioned a while back that when you do the unwrap, you get the original angle is at omega equal to 0 could be far from where it really should be. So here I'm going to just readjust it. I'm kind of cheating a little bit. I'm readjusting this so that it actually, I should technically only bump it by integer multiples of 2 pi, but what I'm doing is I'm centering it at omega equal to 0. And technically that isn't always allowed, but here it will be fine. So it's that step that I went through all of this rigmarole of fixing the value of pi, creating my omega so that I go through 0, finding where the omega equal to 0 point is, also I can use it right here. And then the rest is just labeling and setting line widths and fonts and so forth. And then I do another hold on at the end here. And then I say I can do similar things for n equal to 60 and n equal to 120. So I would reset, I'd keep b the same, I would reset n equal to 60, and from that point down I would all the way down to here I would redo it. Now I don't need to have hold on run again, but it wouldn't hurt to leave that in there. So I would do that for n equal to 60. I would do that for n equal to 120, each time with a different color for my line. And then at the end I use a command called legend, and that will put a nice little legend on my plot that I can later move around if I want to, that will tell what the different lines are. So it keeps track of the fact that you've plotted something solid, something dashed green, something dashed blue, and you put in the text that you want associated with those line types, and it will make the legend command. If you want more info on that, just type help legend and you'll get it. All right, let's move on slide. Just want to point out that we almost always, that's why I say always in quotes, always plot our magnitudes in dB. That's how real engineers tend to look at their filter designs. We hardly ever I say hardly ever, but occasionally. But the trend is to not use a log frequency axis. Although technically I can see an advantage to doing that sometimes. You obviously would only be able to plot one side of your frequency response if you're going to use a log axis, because you can't get down to 0 and you can't do the negatives, at least not easily. When we plot these and we look at their plot in dB here, we can see that things don't look all that great. So here we've done m equal to 30 and m equal to 120, and we can see that at least in most of the pass band things look pretty good. Not a lot of up and down there, but notice that right at the edge of the pass band, as we've seen before, the biggest ripple is right at the edge of the pass band, and it doesn't get, that maximum ripple doesn't get smaller for this design approach as M gets bigger for just this pure truncated sync approach. And look at these stop bands for M equal to 30. That's a horrible stop band, and even for m equal to 120, I mean, we're just barely getting down to 40 dB of attenuation by the time we get out to 0.8, and remember our pass band goes out to 0.6. So these are pretty crappy filters, and we need to find a better way to design filters. But like I said, sometimes these are just what you need, and you just need them quick. You just need a quick filter. You don't really care too much. So this is a good approach to that. And this is the pure truncated sync. We create a sync and we truncate it. That's it. We'll now try to improve upon this. And we will now do a windowed truncation method. And so we've just illustrated that the truncation method, it's got a little bit going for it, but it doesn't really give us very good designs. And then we think back to when we studied DFT processing in the previous unit, and we saw that when we truncated signals and then we tried to compute DFTs of them, that we saw some issues with with side lobes of the window function, causing some problems from the rectangular window function. And in fact, the idea here is really not that different. We think about having a desired frequency response with its impulse response, and we're windowing it. We're applying a rectangular window, and so back in the frequency domain, it would be the desired frequency response convolved with the window's frequency response. And we saw in the FFT and DFT analysis sections that was a problem with the rectangular window. And so maybe it would make sense to try this with some other window shape. And that's exactly what we can do. So, excuse me. Just elaborating on this idea, we see that we've got this in the time domain times a window function. And if we think about that in the frequency domain, we would have our desired frequency response. And I put a tilde on it to account for the delay part of that. So that's not a big issue, just a notational issue. And so that thing ends up getting convolved with the Windows DTFT. And we've seen that this convolution causes smearing of the desired frequency response. So we really want this shape, but the thing that we get is going to be some smeared version of this. And that smearing we're seeing show up as a couple different things. We're seeing excessive ripple in the passband, especially right at the edge. We're seeing excessive stop band heights. That's because of smearing in the stop band. And we're seeing a fairly slow transition from passband to stop band. That's because of main lobe smearing. And so the thing that's causing this smearing is the DTFT of the window function. And for the rectangular window, we've seen already, we get something that looks like that, which is sink-like. And so look to see, we've seen this picture before, back when we were talking about doing DFT processing, but same kind of idea here. Suppose this is our desired frequency response, nice ideal low-pass filter. And suppose we want to see what will we get at pi over 2. So we would take our window DTFT, shift it by pi over 2. So now this main lobe is centered right there. Our cutoff frequency is pi over 2. That's our design to cutoff frequency. The product of these two things gives us something like that. And then we integrate that and we get this number. And so if we were to move this just slightly to the right, even just a little bit, we would, so suppose we're trying to find out what value do we get in our design right at that frequency. This thing would get moved to the right just a little bit and we would still integrate it. So we would lose some of this, so we wouldn't have quite as big a chunk there, and we'd get just a little bit more chunk there, and that's what we would integrate, and we would get that number there, which is not 0, and in fact it's still pretty high. It's like 0.2. So that's where the issue comes from. We get ripple in the pass band, we get ripple in the stop band, and the main lobe width causes this transition to be fairly broad. And so all of these things can be fixed to some degree with trade-offs by choosing windows that are non-rectangular. Now remember, when we do that, we are, by the very nature of this, when we go to these other windows, remember they have a wider main lobe, but much better side lobe. So we are actually going to see a worsening of that transition, but a much better side lobe behavior. And if you remember, we saw that the worst case ripple does not get better as the length of the filter goes up. Sorry, I'm back. I had to take that phone call. Trying to keep track of where my daughter is. Okay, so yeah, so what we were seeing is that as we increased the length of the FIR filter, the worst case ripple and the worst case in the pass band and the worst case stop band height didn't get better, but the transition band did get better. So here's our approach. We pick a window to control the pass band ripple and the stop band ripple through the side lobes of the window's kernel, and then we choose the length of the filter to get the desired transition band. So that's kind of how this design approach works. But again, even with the window, this is still not the preferred design approach, but it's better, and we're getting to something that's conceivably workable. So we can see that with the rectangular window here, we can increase the length, so the main lobe gets narrower. The side lobes in general get lower, but notice, as I've been saying, so these all get lower, but this worst case one never changes. So in a sense, the side lobes don't really get lower. That's why I have in quotes, the worst case side lobe does not get lower. Sorry, I'll be back. Okay, I am back from that phone call. It's summertime and my daughter is out of school, and I have to drive her around to various places. Anyway, that's all set. Okay, so the side lobes don't really get lower. The ones farther out do, but the worst case doesn't. Height of the main lobe goes up as n. That doesn't really matter that much. But the most important thing here is that the width of the main lobe gets narrower as n goes up, and that will be true for any of these windows. So as I said, the design approach is use the window shape to get the side lobes down to where you want, the worst case side lobe down to where you want, and then pick the length to get the transition band how you want. Okay, so let's go on here. So here are a bunch of different windows, some of which we talked about back when we were doing DFT. Two of them here are ones that you've not heard the names before during that discussion. So we've got the Hamming, we've got the Hanning, the Blackman, Kaiser, Bartlett. Those are all ones that you've seen before. A couple new ones are the Tukey and the Lanxos. So just in passing, Tukey is one of the two guys who first developed the ideas of the FFT algorithm. So claim to fame there. Anyway, Hanning and Hamming windows are kind of bread and butter here. The plot at the bottom shows the Hanning window for m equal to 31 and m equal to 61. So m here is the length, not the order. This picture is from Proaicus and Monolachus. Okay, so just gives you an idea of pushing down the side lobes, but also increasing the main lobes. Remember, we saw that windows like Hanning and Hamming have main lobes that are twice that of the rectangular window. So the transition band would be twice what you would have as with the rectangular window. So you'd have to increase the length of your filter significantly to probably double it to get back to the kind of transition band that you would get with a rectangular window. So all of these things can be manipulated to ultimately arrive at a reasonable design, not necessarily the most efficient filters, but actually pretty decent designs if you work at it. And for a long time, this was kind of the bread and butter design approach. So this is just showing some of the other windows, what they look like. This is just the DTFT of the actual window. We've seen these kinds of things before when we did the DFT processing. So we've got the Hanning window, which we just saw on the previous page, the Hamming window, and the Blackman window. Remember, the Blackman window has even wider main lobe than the Hanning and the Hamming. Hanning and Hamming are twice the rectangular. Blackman is 4 times the rectangular main lobe. So anyway, so you can get some good designs this way. You can push your ripples down as far as you want, really, by trying different windows. And remember, the Kaiser window allows you to set whatever level you want and actually achieve that. So these give decent designs, but not necessarily the most efficient. So if computational complexity is not an issue, this is a decent design approach. If it is, then we'll see something later that will help us get to really, really good designs. So here are some designs. This was for filter length m equal to 61. These pictures are from Proaicus and Monolachus' textbook. And so this is our standard, the rectangular window FIR design. I forget what the target was here. It looks like the target might be 0.1 pi. Keep in mind the way that most other authors normalize is pi gets normalized to 0.5. So 0.5 goes to pi, 0.1 goes to 0.2 pi. Yeah, that's why I don't like to normalize this way. My normalization, this would go to 1, this would be 0.2, and it's much easier to see it. Anyway, all of these have the same goal for the cutoff. In fact, they start with the same impulse sync function kind of thing. And you can see what the trade-offs are here. These are all for the same length. So remember that the highest side lobe level will stay the same regardless of length. So so here's the highest side lobe level here. Here's the highest side lobe level here. So you can see that you can adjust that by picking a different window. And then if this is too broad of a transition, say we wanted a side lobe down that far, we can increase the filter length to tighten up that transition band width. Okay, so nonetheless, we see that we get a fair amount of ripple up here, and we get some pretty bad stop bands. But with Blackman, Kaiser, Hamming, we get some pretty nice flat pass bands, and we get some pretty low stop bands. So fairly decent designs. So the nice thing about this is with MATLAB, you don't have to actually do too much of the actual computation. You don't have to compute that sync function and shift it and all that. It's all done for you. And in fact, it's done for you for more than just a low-pass filter. So there is a command called FIR1, F-I-R-1, in MATLAB. And if you type help FIR1, or if you want even more information, you can go to MATLAB's more complete documentation available right through the MATLAB command window. There's a help icon that you can click on and get much more detail. But this is the basic idea. There's a variety of different ways that you can call FIR1. So the basic way is going to design by default a low pass filter. The n value that you put in here, keep in mind, is the order. So you'll get a length n plus 1 design. B is the vector that will contain the coefficients. So those are the little b values that we've been talking about. W sub n is what you use to specify the cutoff frequency. And the way MATLAB tells you about that is it says that it has to be between 0 and 1. And they say with 1 corresponding to half the sample, excuse me, half the sample rate. So 1 corresponds to fs over 2, 1 corresponds to pi. So if you want a half band filter with a cutoff frequency of pi over 2, you'd put in a Wn of 0.5. Notice that you don't have to even know what the sampling rate is to design these, and in fact sometimes you don't know what the sampling rate is. You're designing to a specific discrete time frequency that you may not even know how that gets mapped to a corresponding appropriate continuous time frequency. We saw that this design gives us a 0.5 at the cutoff. That 0.5 corresponds to a minus 6 dB. So if you really want the cutoff to be at minus 3 dB, you kind of have to play around with this a little bit to get it right. So it could be a fairly tedious iterative design process to get exactly what you want. And that's one of the big drawbacks to this design approach, is that it's not that straightforward as how to get exactly what you want. Remember, we spec'd out our deltas for the ripple and the stop band, and pass band cutoff and stop band cutoff. You see that you don't spec those here. You're just giving an n and you're giving a w sub n, and it's kind of up to you to iteratively play around with this to get what you want. But not a bad design if you're willing to tweak it and play around. And you can also tell it, I'd like a high pass, I'd like a band pass, I'd like a band stop. And you can also design multi-band filters. So you can give it a bunch of different band edges, and it will create pass bands and stop bands alternating between those. So if you put in quotes DC minus 1, the first band will be a pass band, and then it will flip back and forth between pass band, stop band, pass band, stop band. And if you put in DC minus 0, it will make the first band a stop band. So then it will be stop band, pass band, stop band, pass band, and so forth. So where does the windowing come in on this? For all of these specifications up here, we didn't specify what the window was. And the default window is the Hamming window. But if you want to specify what the specific window is, then you can put in your specific window call there. And there are some examples of how to do that and how to combine this idea with these ideas. So in classic MATLAB form, there's a lot left to, there's a lot of different ways that you can call most MATLAB commands, and that's probably one of the most challenging parts of learning how to use MATLAB. So we'll stop there for this set of notes, and I will see you in the next set where we'll talk about yet another way of designing FIR filters, but still not the ultimate way to design them, which we'll see even after that one.